Okay, we're discussing chapter 5 of conceptual physics, Newton's third law of motion. Um, Here we go. We're in this lecture. Let me dismiss this so uh, it doesn't disturb the screen. Um, this lecture will help you understand the forces and interactions, Newton's third law of motion, vectors, and the third law, and a summary of Newton's three laws of motion. We're going to go through, and since this is the last law, we're going to go through all three laws of motion. So let's forces and interaction. Interaction is between one thing and another. And so it requires a pair of forces acting on two objects. Example, interaction of a hand and wall pushing on each other. A force pair. You push on the wall and the wall pushes on you. So it, it just feels like you're pushing on the wall, but if the wall weren't pushing back on you, you would fall straight into the wall. So there is it's pushing back on you. Whenever one object exerts a force on a second object, the second object exerts an equal and opposite force on the first. So you strike a hammer, the peg will actually have force against the hammer, and that's what brings the hammer to a stop. Okay, a soccer player kicks a ball with 1,500 newtons of force. The ball exerts a reaction force against the player's foot of A, somewhat less than 1,500, B, 1,500 newtons, C, somewhat more than 1,500, or D, none of the above. Well, it's B. It's going to be exactly the same amount that the player's foot exerts against the ball. Okay, action and reaction forces. One force is called the action force. The other force is called the reaction force. They're co-pairs of a single interaction. Neither force exists without the other, and they're equal in strength and opposite in directions. They all act on different objects. Just like you have your hand on the wall, you have the wall on your hand. Your hand and the wall are two different objects. Okay, the re-expression of Newton's third law. To every action, there is always an opposed equal reaction. Example, tires of a car push against the road, and while the road pushes against the tires forward, the road pushes the tire forward. From the friction, I think I was supposed to link a video of what happens when there's no friction. I'll try to remember to do that on Canvas. Okay, simple rule to identify action and reaction. Identify the interaction. One thing interacts with another. The action, object A exerts a force on object B. The reaction is object B exerts a force on object A. An example is a rocket exerts force on a gas, and the reaction is the gas exerts force on the rocket. It's the expulsion of the gas that gives the airplane thrust. Okay, when you step off a curb, Earth pulls you downward. The reaction to this force is a slight air resistance, non-existent in this case. You pull the Earth upward, or none of the above. Actually, as crazy as it sounds, it's C, pulling the Earth upward. Now, remember, force equals mass times acceleration. So when you step off the curb, you have a gravitational acceleration pulling you downward. Now, you have the same pull of the Earth towards you, but remember, force equals mass times acceleration. So the acceleration is the same, but the mass of the Earth is so massive that it's negligible. But you are pulling the Earth up towards you. And we'll see that more when we get to Newton's universal gravitation law. Okay, when you step off a curb, Earth pulls you downward, and you pull the Earth upward. Why do you not sense Earth moving up towards you? Well, I pretty much already answered that. Earth is fixed, so it cannot move. Earth can move, but other objects on it prevent it from moving. It moves, but by an imperceptible amount. Or D, none of the above. Well, I've already answered it. It's C. It is such an uh, in infinitesimal amount that it's not perceived. The force you exert on Earth is equal in magnitude to the force Earth exerts on you. You move more than the Earth because Earth's mass is enormously greater than your mass. Remember that Newton's second law tells us that acceleration is inversely proportional to the mass. Earth's tiny motion is less than you can perceive. Um, okay, let's see. Now, action and reaction on different masses. The cannonball force divided by mass gives you an acceleration. The cannon force divided by a mass gives you the same acceleration. The same force exerted on a small mass produces a large acceleration. The same force exerted on a large mass produces a small acceleration. This is, if you've ever fired a rifle or a pistol, this is the recoil. You fire a pistol and the bullet accelerates out the front of the barrel at with a very high acceleration. The mass of the bullet compared to the mass of the pistol is the pistol is much greater, so it pushes back, but to a lesser degree. I remember firing a pretty large pistol. I think it was a 44 Magnum, if I recall. And that thing, I fired it once because it was very, very. It had quite a kick to it. Okay. When a cannon is fired, the accelerations of the cannon. Oops, gave the answer away. When a cannon is fired, the accelerations of the cannon and cannonball are different because A, the forces don't occur at the same time. B, forces, although theoretically the same, in practice are not. C, the masses are different. And D, the ratios of force to mass are the same. And it's C, the masses are different. The cannon is much more massive than the cannonball. So the acceleration is different. Okay. When a cannon is fired, the accelerations of the cannon and the cannonball are different because did I just do that one? I must have pushed the up button. The masses are different. Okay. Consider a high-speed bus colliding head-on with a flying bug. The force of impact splatters the unfortunate bug over the windshield. Which is greater, the force on the bug or the force on the bus? Well, if we believe Newton's third law, both forces have the same magnitude. Although the forces are equal in magnitude, the effects are very different. Do you know why? Once again, it comes down to the mass. The mass of the bus is so much greater than the mass of the bug. Okay, two people of equal mass on slippery ice push off from each other. The key here is they're equal mass. Will both move at the same speed in opposite directions? A, yes. B is yes, but only if both push equally. C, no. And D, no, unless acceleration occurs. Now, it really wouldn't matter even if one of them didn't push. If one of them, if they're on ice and they're the same mass, if one pushes and the other one stays still, they're both going to go in opposite directions. So they will go at the same speed in opposite directions. Yes. Now, if one of the skaters was more massive, the lighter one would be propelled backward with a higher velocity, and the heavier one would go with a slower velocity. Regardless of how the people push, the forces they exert on each other will have equal magnitude. Since equal magnitude forces acting on equal masses produce equal accelerations, both people achieve equal changes in speed. Okay, define your system. This it can be a little confusing to students. I'm not gonna. It's not. Um, it can be confusing, is all I'm saying, and I'm not gonna rely on your understanding of it to a great uh, deal. Define your system. Consider an orange on a cart. An applied external force causes the orange to accelerate in accord with Newton's second law. The action force is depicted here by the red vector. Now, the reaction force, consider the orange and an apple pulling on it. Action and reaction do not cancel because they act on different objects. The external force by the apple accelerates the orange. Now, if you consider the apple and orange together as the entire system, the apple is no longer external to the system. The force pair is internal to the system, which doesn't cause acceleration. So the system isn't accelerating. The action and reaction within the system cancel. If there were no external forces, the system would not accelerate. The apple's feet push against the floor using friction. So the floor must push back against the apple, providing an external force. The external frictional force exerted by the floor on the apple's feet can accelerate the system. So it's the system of just the orange and apple they don't cause an acceleration, but the feet of the apple, sounds funny, feet of the apple on the floor, they cause the acceleration. Okay, the apple and orange system will move with constant speed. If the, give it again. The orange loses mass, the apple gains mass, another external force counteracts the friction force on the apple's feet. None of the above. And I already gave it away. It's C. Floor friction acting on the cart's wheels or the drag force produced by an opposing wind would be examples of such external forces. Let me read that again. Floor friction acting on the cart's wheels or the drag force produced by an opposing wind would be examples of such external forces. Okay, consider the flight of a helicopter. When lift is greater than the helicopter's weight, the helicopter will move upward, move downward, hovers in midair, none of the above. Well, if the lift is greater than the helicopter's weight, it's going to move upward, B. And that's the case. Okay. A bird flies by counteracting the Earth's magnetic field. Well, that's not the case. Pushing air downward so that the air pushes it upward. Hovering in midair, inhaling and exhaling air. Well, that's B, pushing downward so that the air pushes it upward. Okay. Slightly tilted wings of the airplanes deflect oncoming air downward to produce lift, oncoming air upward to produce lift. Both A and B, or neither A and B. Well, it's downward. It's A, oncoming air downward, but there's going to be more to it. I think we'll get to it if we study the Bernoulli effect. But their explanation is a wing diverts air downward by exerting downward force on the air. The air accordingly exerts upward force on the wing, called lift. Horizontal forces exerted on the wing by air are called drag forces. Okay, compared with a lightweight glider, a heavier glider would have to push air downward with greater force, downward with the same force, downward with less force, or none of the above. Well, if it's a heavier glider, would have to do it with a greater force. The force on the air deflected downward must equal the weight of the glider to maintain altitude. Okay, vector components. We've had a little bit of vectors. We did it with, like an airplane flying at a fixed speed into a crosswind. So we studied these slightly. This is just a variation on those same topics. Vertical and horizontal components of a vector are perpendicular to each other, and they're determined by resolution. If you have this vector here, the velocity of the stone, it has a vertical component and it has a horizontal component. Those two components, you get the square root of the sum of the squares, and that's equal to the velocity of the stone. And we can see, we'll see later when we study projectile motion that the horizontal velocity is going to remain constant, but the vertical velocity is going to decrease. I mean, it's going to change. You throw with an initial velocity up, by the time it reaches the peak, it's zero velocity, and then it starts to go downwards simply from the gravitational acceleration. Here we go. Nellie Newton pulls on the sled as shown. Which component of her force F is greater? Well, if you just look, she's pulling at an angle. This one is the larger of the two, and the vertical one is smaller. So the horizontal component, Fx, is greater. What other forces are not shown on the sled? Well, you have the gravitational force and the normal, the weight mg and normal and also act on the sled, but they're equal, so that it doesn't add to the acceleration. Let's see. Two forces act on the block of ice. As the ramp is raised, which force remains constant? Well, the gravitational force mg is going to be the same. Now we'll see that the normal force is going to change, and the component parallel to the surface is going to change too. But the force that remains constant is the gravitational force mg. It's going to be the same. And okay, as the ramp is raised, how does the magnitude of n change? Well, when it's horizontal, you've got maximum mg. As it's tilted, mg is going to be decreasing by a factor, and decreases with increased angle ramp. And I'm going to show you a demonstration of that in a little bit. When the ramp is raised 90 degrees, what is the net force on the block? Well, it's mg. It's we're assuming no friction on the block of ice, so it's fully mg. The net force is mg. Okay. Can you see the normal and mg are equal and opposite? They're equal and opposite here. The normal, this actually should be smaller than this one, and it's less on the incline because it's reduced by a factor from the angle. Can you see that the resultant of N and mg is the force propelling Nellie downward on the hill? And can you see which component of mg is equal and opposite to N? This component is opposite N. Now, I'm going to switch shares. I'm going to go to new share. I'm going to go to Mathematica. Mathematica is a great, that's not the one I want. Let's see. Where's my Mathematica? Mathematica, here it is. Now, it's in an opposite direction, but let's go all the way to 0. Now there's no horizontal direction here, and you can't see the vertical component, but it is equal to the normal force. Now, as I start to raise this angle, you'll see that this side parallel to the surface, to the sliding surface, it's going to increase. So let's do that again. Watch that purple, and that's mg sine theta. It's increasing. It's increasing. So it increases. The factor is the mg sine theta, or is a sine theta reduction. And I can't, if I take it all the way to 90, I can't, it gets an error. So it goes up to 89 degrees. And it's almost fully mg. Now notice let's look at what happens to the normal force. Uh, as I raise it, the normal force gets smaller and smaller and smaller. That's this blue line here, to where it's almost negligible here when it's almost vertical. Okay, so there's a dynamic way of showing how these angles increase and decrease. So the normal force is reduced by a cosine theta factor, and here the sliding force increases with a sine theta factor. Okay, I thought that was a good little demonstration, dynamic demonstration. I did not write this code. In fact, I don't know who wrote it. There's a Mathematica provides you with a whole bunch of demonstrations. I just copied it from the demonstrations pages from Mathematica. Okay, well, I think that's it for this demo. Let's go back to the PowerPoint, Microsoft PowerPoint. There we are. So we saw that the n decreases as the slope increases. Okay, I think Newton's first, this is a summary of Newton's laws. Newton's first law of motion, the law of inertia. An object at rest tends to remain at rest. An object in motion tends to remain in motion at a constant speed along a straight line path. And that's, in the absence of any external forces, it's going to remain in a straight line motion at a constant speed. Newton's second law of motion, that when a net force acts on an object, the object will accelerate. The acceleration is directly proportional to the net force and inversely proportional to the mass. Not only is it directly proportional to the net force, it's in the same direction. The acceleration is in the same direction as the net force. And then Newton's third law of motion, whenever one object exerts a force on a second object, the second object exerts an equal and opposite force on the first. And I think that is it for this particular Good point to start. I got to go to the